Right. Um, right. Today we are in kinetic energy. Right. Kinetic energy. Kinetic energy. Right. Right. So kinetic energy usually is written as EK. Okay. So usually it is written as EK. Uh, and sometimes it is also written as KE. This is how it is written. Right. Now remember, kinetic is energy is there stored in an object due to its motion, right? Due to the motion. Due to the motion, an object can may have kinetic energy, right? And the thing is, the faster the object moves, right? Faster than object moves, the kinetic energy is also increasing. The faster it moves, the kinetic energy also goes up, right? Now remember, uh, for example, we have an object somewhere. Let's say it is on this mountain top, and it is now falling down from that cliff, right? Now, since this object is falling down, when it is falling, it is getting what? Velocity. So we did some with the velocity equations, right? Due to the gravitational force, it is accelerating downwards. Therefore, velocity is also increasing. So when the velocity is increasing, it is gaining the kinetic energy. So using that, the scientists have derived an equation E equals half mv squared, right? So this is the kinetic energy equation. Now kinetic energy is measured in what? Joules. This is mass, it must be in the SI units. And here it is velocity measured in meters per second, right? Okay. Okay. Now let's derive the kinetic energy equation, right? Deriving kinetic energy equations. Now remember, now we can use force to accelerate an object. For example, let's say this object is on the ground. Let's say it's having a mass m. Let's say it is a sphere of mass m. And what we do is, it is at the beginning, its velocity is 0. And we are with the force, if you can remember, we are doing some work on it with force. And because of this force, this object is gaining some velocity. Same object, it is gaining some velocity starting from v0, and here it is gaining velocity, right? And we are doing some work on this, and the work, so when the object has moved from here to here, it has traveled a distance of d, right? So it has been accelerated from here to here, right? When we are doing this acceleration, it has traveled d distance, right? Okay, right. So dispersion, and the work is done with a force, right? Can you write an equation for the work done on this object using, now with your previous lesson you can remember, right? With force, with d, uh, right, with force and d, write me an equation for work done on this object, and yeah, work done on this object. What is the work done on this object with force F? Yeah, we have applied this force for a distance of d, right? Displacement is d. Until it has covered d distances, we have applied the force. So it has accelerated from here to here until it has gained the velocity of v. Yes. So what is the formula for it? The work done on the object is equal to what? Huh? The work done on the object W equals F into D. Right? Can you remember that? This is the work done on the object. Right? Work done on the object is equal to the, now it has gained, let's say all the work done on the object has given the object the kinetic energy. Kinetic energy. Right? So FD equals KE. Right? Now, if it has gained V velocity, right? Uh, using D, right? Using D and V, derive an equation, right? For velocity. Derive an equation for velocity using V and D. Can you do it? And acceleration A. Acceleration is A. Derive an equation for velocity. Can you do it? derive an equation for velocity using A and B. So we have done that, right? We have done that in the first lesson, few lessons, right? Over M, say what is the equation? V equals V V squared equals U squared plus 2A's. I told you it has started the journey from zero velocity. So therefore V equals 2A, displacement is D, right? Right. Now we are trying to derive an equation for kinetic energy, right? Now, now how many formulas we have? There's one, and we have another formula for V equals 2AB, uh, and we can derive another equation, what? F equals MA, third formula, right? Uh, Using these three formulas, right, I want you to derive a formula for kinetic energy using M, derive V, using M and V, derive a formula for kinetic energy using M and V. Using the, you can use the above formula as for derivation, but in your final formula for kinetic energy, you must have only M and V. For the derivation, you can use the three. Now you should derive it and send, derive it. That's the formula, right? We are trying to derive it. I want you to tell me the derivation, how it is derived. Not that hard actually. Everything needed is here. Right. Let's look at the derivation. It's not that hard actually, right? So let's right. So so kinetic energy is equal to Ft. So first of all, write it down. F and D. Now we want to add what? M and V. So therefore, we can replace F with MA. See, MA equals, and we can replace D with what? This one. Here we have derived V equals square root of 2AD. So it means if you make D the subject here, you get it as what? V square divided by 2A. V square divided by 2A. So we can plug it here. V squared 2A. Right? Now half cancelled. So we are getting half MV squared. So this is a derivation. This is not the only way of doing it, right? You can come up with different ways, but still at the end of the day, this is what we get. So this is how it is derived. I hope it is clear, right? So no need to memorize these things. these derivations. Okay. Okay. Uh, I will give you another question. This is easy now. Just you just need to plug in values. There's a body traveling at 12 meters per second, and it has kinetic energy of 1650 joules, and it can increase the speed up to new speed 45 meters per second. Find new kinetic energy. Find it. Yeah, let's look at it. So they have mentioned. So we just have to find the mass. Yeah, that's the answer. Now here the catch is to find the mass. To find the mass, you can use the previous kinetic energy. Kinetic energy is equal to half mv squared. So it is. We can make m the subject. 2 ke divided by v square root. Right? And new speed is given like this. So here kinetic energy new one half same mass is not going to get changed. So half mass is here 2 ke velocity. This is half m, and we have the v squared. Uh, so just plug in the values now. The harder part is over, right? Square root of 2 kinetic energy is 1650. The new velocity is given as 45 multiplied by, so it is inside this root 45 multiplied by 45. With this you can find the answer in joules. Here as you mentioned the kinetic energy is 23,000. Right. uh, Now we can move on to a new subtopic: gravitational potential energy. Gravitational potential energy. Right. Okay. Let's move on to that. right? So gravitational potential is energy and the kinetic energy is most of the time interrelated, right? So gravitational potential energy is usually with the symbol it is given with delta E equals uh, GRAV. That is how it is usually written. Gravitational potential energy. Or you can write it as EP. Kinetic energy is KE. Gravitational potential energy is EP. Now, for example, if you have an object and a hilltop, the object having mass is lifted onto the hilltop. The hill is, let's say, it is h in height. The amount of potential energy stored of this object is equal to EP equals mgh, right? So h means actually we are calling it as change in potential energy. Why? Even once it was in the ground also it has some potential energy. Remember why? The gravitational attraction is coming from the center of the earth, right? So even when we are at the surface on earth, there's a potential energy stored in us, right? So once we go higher, so it means what? More potential energy is stored. So that is why we can only measure the change in potential energy, the amount of potential energy stored by on the ground itself. Also, there was a potential energy on the hill. Also, there's potential energy, stored potential energy. So therefore, there's a potential energy difference between these two places. So that is why this EP equals mg delta H, right? Units are the same. G is the uh, acceleration, gravitational acceleration. M is the mass in kilograms. H is measured in meters, right? Okay. Now remember, when we are doing this calculation, we are assuming the gravitational field. There's a field, just like an electric field. There's a gravitational field. So we assume this field is constant throughout, right? The assumption is gravitational field is constant, right? Assumption gravitational field is constant. That is the assumption. Gravitational field is constant throughout. Right? Why? Because there can be a slight, actually, the gravitational field is decreasing when we go up. So, therefore, G value is actually not constant. The gravitational acceleration while the object was on the ground and while the same object was on the hill, the gravitational acceleration is not constant. So G value is actually not maintained. But here we are assuming the G value is maintained constant. The G value over here and the G value over here both are the same. So why it's the same? We assume the gravitational field is constant. But actually it is not constant. There's a slight infinitesimal difference between them. When you go higher and higher, the gravitational field is getting weaker. That is why when you go further up, right, we can break free from the gravitational field. So that is what the satellites and rockets are doing, right? Okay, all right. Uh, let's continue from here, right? And also this increase in this potential energy can also be named as what? Stored potential energy. And also you can tell this potential energy has been stored by a work done on it. And if you can remember, see, we have to put a force on this object, and then using that force we can take it here. So there's a force, there's a distance. Distance is h, right? F into h, right? So there's a work done on the object. So you can tell in another way, F into delta h. Work done on this. Without using this force, we can't take it to here. Right? The force done on this object is equal to the potential energy stored. In that way also you can tell. So these are different interpretations. All these interpretations are correct. I am telling you these things in the question. They can ask you in different ways, right? Work done on the object. This the work done on the object is equal to stored potential energy of the object. Right? So in different ways they can ask the same thing in your question paper, right? The potential energy transfer. Uh, Again, now I think I have given you enough information. Using this information, let's see, I'll give 1 minute. Derive this equation. Can you derive this equation? I have given told you enough information. Can you derive it? This formula. Using the given information. Let's see. Do these things. Right? So one way or the other way, if you can get the derivation. Derivations are easy. Another thing is you know you got the right answer. And if you can get the expected formula with the given symbols, you know you have the answer, right? So correct answer. So you can tell again as we discussed, work done is equal to stored kinetic energy, stored potential energy EP. So EP equals work done is equal to F into S in this case delta H. So force we know, we are, let's say now the we are keeping the object at, we are taking it slowly or at constant velocity. So therefore we can apply the first law of Newton. First law of Newton, it means F minus mg equals, there's no acceleration, right? We are taking it up with constant velocity, right? So therefore force is applied is equal to mg. The object is in equilibrium, because if we consider a velocity to this object, then it has two energies. So the work done is equal to both potential energy stored and the kinetic energy stored. But here we are assuming we are taking it up slowly or at a constant velocity to here. Therefore, no change in kinetic energy is there since we are taking it up with constant velocity. And since it is moving and moved at constant velocity, we can add the first law of Newton, that is when an object is in equilibrium, force applied is equal to forces are balanced, right? Okay, so F equals mg. So mg delta H. Right? The assumption is the gravitational field uh, at these lower distances. So we are assuming this distance is very low. Now remember, in the planetary cosmic scale, even 100 meters is considered as a little distance. Right now, when we are talking about this gravitational field, we are talking about the cosmic scale, universal scale. Right? These potential energies are changing between planets, orbiting around the sun, Earth, galaxies. So compared to these distances between planets, right, even a 1 kilometer distances can be considered as a very little distances. So during these very little distances, the gravitational field is considered constant. But remember, if you are taking this object a few kilometers up, then that gravitational field change should be considered. So that is why later you guys are learning about what? A different formula for distances travel beyond that level. For that we can't use this formula. I remember these are only uh, near the Earth's surface, and the distances traveled are very short distances, right? So if you are taking the object very further distances, then you will have to derive a different formula for this, right? So yeah, so for different condition, different formulas must be derived, right? So this is for normal classical physics, Newtonian physics, right? Okay, I will give a very easy question here, right? Now I will use a diagram. It's a staircase. The height of the staircase is 3.7 meters. There's a man climbing the staircase. The mass of the man is 74 kg. Right. Now I want you to find the change in potential energy of this person. Fine. Very easy. Right. So this is the answer for this very easy answer. Uh, Very easy question actually. Right. Okay. Now we are done with that too. So now we are moving on to principles of conservation of energy. Principle of conservation of energy. Okay. Right. Uh, the principle of conservation of energy. Uh, right. So it's kind of like O level stuff, right? So basically, it says the energy cannot be right. Now remember, there's an assumption. It's a closed system. This principle can be applied only for a closed system. Closed system means in the chemistry course we are discussing. This is the system. This is the surrounding. No mass change is happening. Only energy change is happening between the surrounding and the system. Energy and energy change is happening. No mass change is happening. If the mass change is also happening between the surrounding and the system, it is an open system. Right? If there is no change whatsoever, no mass or not even energy, it is an isolated system. Here we are taking it as as a closed system. The same thing, the same assumption that we are using in general chemical calculation, especially in the physical chemistry stuff. Enthalpy is likewise closed system. Right. So in brief, so it says total energy. For example, if you have a computer, let's say PC, you are using a certain amount of current to power this up input, and you are getting an output, the things that you are getting done, and the light it is producing, the sound it is producing, right? Light, sound, uh, and the vibration, everything, right? Movements, everything. So that's the output of the computer. So energy is put in and the energy is released as the output. So the same energy we inserted is equal to the energy released. Same energy amount is inserted and the same amount is released. So it's a conservation of energy. Why? No energy has been added in. So we can't create energy. What you have given is taken out. No energy has been added or deducted. So it's a conservation of energy. So you can tell in brief, total energy in is total energy out. So there's no difference between the no difference between energy in minus energy out. Energy out. right? So you can tell about it in different ways. This is not this is an O level theory, right? So in most of the chemical calculation, physics calculations are done based on this. This is not just an assumption. That is how our universe is designed, right? So it's a physics law. That is how our universe is created, or that is how it started to appear. Our universe. We don't know what the reason is, but for some reason it has started to appear. Right? We think as Big Bang, so we don't know what was there before the Big Bang, right? As per science. Oh, yeah. So remember now, when we are doing any calculations on, so we are later moving on to oscillations, right? Simple harmonic oscillations and waves. So all these later lessons are directly or indirectly connected to the mechanics we are discussed. Even electricity is connected to mechanics. All these formulas and theory that we are using later at the electricity, waves, and the thermodynamics, all these lessons, and even the theories that we are discussing in chemistry are all direct applications or derivations of the mechanics that we are learning, right? So therefore, now we are at the final parts of the mechanics. So as a direct application of this conservation of energy law, we can apply the same principle into in oscillations. We are talking about swinging pendulums, right? Swinging pendulums. And objects in free falls, right? And and you can apply into some scenarios like skiing, uh, basically into every sport. They can give you questions based on the scenario, so you can plug in. So all these theories are interconnected actually, right? Right. Let us start off with a question. It's on skiing. Let's say now they can fabricate some information. Some of the information is sometimes even not vital, right? So you should know which theory to apply. You should be able to filter off some information when you are doing a question, right? Otherwise, just they won't put all the vital information on the plate and let you do it. Then by looking at the information, you can decide on which theory to be applied. No, sometimes they may give you some unnecessary information also. So you should know filter out everything that is not needed and plug in the correct theories and get the answer. Right. So now this is a water skiing person. It is I'm not good at sketching. Going downhill on snow, and it's the same person again skiing, right? Now along this hill, right? He has traveled 750 meters by so far, right? On this snow, on this slope, and the angle of the slope is 25 degrees. Now I want you to find the. So he's starting at zero velocity and at downhill he has gained some velocity. So start off at v velocity 0, and I want to start the u velocity. Plug in the correct appropriate formulas and find the velocity of this person downhill. Right? Fine. Okay, I got an answer. Yeah, I have an answer. Right. So it is. You can do it in different ways. I got an answer. Let's say you can do this in different ways, right? So this is my approach on this question. So what I would do is I would find the amount of change in amount of decrease in potential energy. So delta E potential energy is equal to, so this energy must be transferred into something because the potential has energy has got decreased because he is going downhill, right? So we can assume it is getting transferred into kinetic energy because initially he hasn't got any potential energy, kinetic energy, but he had the potential energy stored. But here, all the potential energies has been converted back into kinetic energy. So KE, so O level question, right? The thing is, now when you plug in the values, it is mgh delta h equals kinetic energy is half mv squared. Now see now m term we can cancel it off. And it's always easy in physics and chemistry both. Before you are plugging in the values, you can simplify your formula first. It makes the answer more accurate and makes the calculation much easy. So before plugging the value, let's make, they are asking us to find V. Let's make V the subject. So it is due to G delta H square root. Now the thing is finding H. Now remember, when we are plugging the potential energies, it must be always the vertical movement. Now 750 is what? It's diagonal actually. So we have to find the vertical distance. So it's sine cos tan, right? Delta H. Uh, yeah. So it is 750. This is diagonal. Sine 25 is equal to delta H. Right? Sine is delta H. So you can straight plug in that. 2G is 10. Let's assume delta H is 750 sine 25. You get the value in meters per second, right? So if you have done it right, so okay, right? You will get a value. So your value is roughly 78.82, right? So I don't mind about your final answer as long as your method is correct. So that's my responsibility, right? How your physics part is okay with this. Other part is your mathematical ability, right? Okay, so they can give you this question in different ways. Sometimes they may tell you now the heart, not all the energy being transferred as kinetic energy, only about a certain percentage is converted. So in that case, you will have to uh, find that percentage that has been transferred and assume the other is being wasted. You can't say it is destroyed. It has been transferred into energy that is not useful in this scenario, like sound energy, light energy, things like that. So they can give you different scenarios, same similar question in different scenarios. So you should be able to use your theory knowledge in physics to tackle the question. So this is all for today, and we will meet next day. So we are going to start the next class with right with power, right? Okay. Bye bye. Take care. All right. So next day is welcome. The next day is about power.